This is section 6.2, and we're looking at theorem 6.2.1. And if we let A be 2 by 2, and again we assume it's in the complex numbers with distinct eigenvalues. Eigenvalues. Lambda 1 and lambda 2, and corresponding eigenvectors. X1 and X2. So we have that, and then we let P equal the matrix made from X1, X2 columns. Okay, so it's 2 by 2 matrix. It says then, so here we have then P is non-singular, and P inverse AP is equal to the diagonal matrix lambda 1, lambda 2 there. So that's a biggie, right? So this says if I find the eigenvalues of a 2 by 2 matrix and they are distinct, lambda 1 is not equal to lambda 2, then I can do this transformation to get a diagonal matrix. So, pretty cool. Okay. So the proof, there's a few things to prove here, all right, because we've got P is non-singular, and then this diagonalizability. Now, it's mostly the non-singular. Once we get that, it's not so bad. Okay, so they say for our proof, so we have A x1 is equal to lambda 1 x1. That's just by what we set up. And A x2 is equal to lambda 2 x2. Oops, there's a 1 there. 2. So again, that's just what we assumed. We said A has these distinct eigenvalues and eigenvectors. So we have that. And then what they want to do is we're going to show sum x times x1 plus y times x2 is equal to 0, has only the trivial solution. So in other words, they're linearly independent columns. Okay. And so once we have that, then we know that our matrix is non-singular. Okay. So they're going to do a proof by contradiction. So we'll assume well, wait, I take that back. I'm not sure they're doing a proof by contradiction. We'll see. I haven't read through the whole proof yet, honestly. Sorry about that. Okay, so we assume that this thing is equal to 0. We have some x and some y that are equal to 0. Now, if that's the case, and we think of that vector there, because it's the zero vector, then certainly A times that vector, since it's the zero vector, is going to give you the zero vector. Okay, so we multiply that. That is A times the zero vector, which is the zero vector. Okay. So now I can multiply through and do a little, so I can do a distributive property and a little associativity. And so multiplying through, I can write that as x, x1, and then plus y, x2. So I can write it like that. But now, remember, we've got our ax1 and ax2, so this is equal to x times lambda 1 x1 plus y times lambda 2 x2. And that all has to be 0. Okay, because that's what we had right up here. And so we have a system, all right? We have x1 plus y x2 is equal to 0, and we have x lambda 1 x1 plus y lambda 2 x2 is equal to 0. Okay, so we have that. And so if I multiply through the top by lambda 1, and actually I'm going to multiply through the top by negative lambda 1. So if I do that, right, and then add it to the second row here, I end up with this process here. Let's see, x2 equals 0. And so I'm going to multiply through this thing. I can write it over here, minus lambda 1 x1 minus lambda 1 y x2. Right, so I get that. So when I add it here to the second row, the first terms cancel out and I get 0, and so I'll just get, with a little factoring, lambda 2 minus lambda 1 times y times x, that's an x2, x2, and that's equal to 0. Well, remember that lambda 2 and lambda 1 are not equal, right? So we have lambda 2 minus lambda 1 is not equal to 0. And we know that x2 is not equal to 0 because it's an eigenvector. And so all that leaves is this implies y equals 0. But then if y equals 0, that implies that x had to also be 0 because of our, x, we would be left with x times x1 is equal to 0. And so only the trivial solution, x equals 0, y equals 0. So that's a pretty neat proof. And so that means P equal this x1, x2 is non-singular. Okay, and after that, not a big deal, because if we start with, you know, AP, then that's A times our vectors x1 and then x2. But we know that that is simply, when we multiply through by that, you know, we'll get A times the first column and then A times the second column. And so that's just our lambda 1 times the first column and lambda 2 times the second column. Okay, so we have that, but that I can rewrite as the matrix multiplication of the p vector times lambda 1, 0, 0, lambda 2. Okay, so these two things generate the same matrix, and so, you know, this is p times lambda I. But so now I have, you know, I have AP equals p times lambda I. Whoops, now I can't really write it as lambda I, can I? Because they're distinct eigenvalues, so I really do have to keep my lambda 1, 0, or just name it a matrix like big lambda or something like that. But I'll keep this, or I could name it D for diagonal. 0, lambda 2, so there we go. Now, since p is non-singular, multiply both sides by p inverse on the left, and we get p inverse AP is equal to our diagonal matrix. And so there we have the proof. So very nice. And therefore we can diagonalize something. Now they have they have some examples where they determine eigenvalues and eigenvectors. They give well, actually they don't determine them, they just tell you what they are, and they go through and show that it works. So you know, there we go. That's our theorem. 6.2.3, right? Let's go back here. No, 6.2.1. So sorry. That theorem.